So welcome back to Manish Kumar channel. Let us do some more problems on complex numbers. So problem number 1, show that a necessary and sufficient condition for 3 points z1, z2, z3 in the complex plane forms an equilateral triangle, that is z1 square plus z2 square plus z3 square is equal to z2 into z3 plus z3 into z1 plus z1 into z2. So if you see the equilateral triangle and the angle between these three are pi by 3, right? Because of the property of the equilateral triangle, right? So how we are going to prove? You see, we are going to see this vector z2 minus z1, and we are going to use the rotation, right? Rotation by pi by 3. If you see, then we are going to write this vector as and this vector using the rotation relation. And similarly, we do for other sides. Okay. So necessary condition, if z1, z2, z3 forms an equilateral triangle, then already I have shown you the picture. So z2 minus z1 is nothing but e power I pi by 3 z3 minus z1, right? So this is going to be your rotation type. Z2 minus z1 is nothing but e power I pi by 3 and then z3 minus z1, right? From this. Similarly, we can get z1 minus z3 is equal to e power I pi by 3 z2 minus z3. So if you see, this is, let's say, call equation number 1 and this is called equation number 2. So if we divide equation number 1 by equation number 2, then we are going to get this, and e power I pi by 3, e power I pi by 3 is common, so it will be cancelled out. And now after solving this using cross multiplication, right, we are going to get these two factors, and then after simplifying, which yields the desired result, right? Sufficient condition, if z1 square plus z2 square plus z3 square is equal to z1 z2 plus z2 z3 plus z3 z1, then we can always go back in the same way, and we are going to get this condition. And when you write by uh, you know division form, you will get this form, and then this implies the sides are related by rotations, right? And proving that triangle is equilateral. Okay. So let z1, z2, zn be complex numbers, then prove that there is a point x in 0, 1 such that modulus of 1 minus summation k equal to 1 to n zk e power 2 pi I k x modulus is greater than or equal to 1, right? So how do we do solution? So since we know the function 1 e power 2 pi I x and dot 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 and so on e power 2 pi I n x, right? These functions are, if you see, these functions are orthonormal, right? These functions are orthonormal on 0, 1. Okay. So in this case, hence, what we are going to get, we are writing integral 0 to 1 modulus of 1 minus summation k equal to 1 to n zk e power 2 pi I kx square dx, which is nothing but 1 plus summation k equal to 1 to in n and modulus of zk square, right? And which is greater than or equal to 1 because since the integrand, right? Integrand is continuous and non-negative. Okay, it must be greater than or equal to 1 at some point, right? So we have done the second problem as well. Now let us see one more problem. Let z1 and z2 be two complex numbers whose real parts are negative or 0, right? Then we have to prove this inequality. Absolute value of e power z1 minus e power z2 is less than or equal to modulus of z1 minus z2, right? So solution. So we have e power z1 minus e power z2 is nothing but integral z1 to z2 e power z dz, right? For all z1, z2 belongs to complex plane. Okay. So now where where integral is taken over any path, right? Connecting connecting them, right? Okay. Suppose z1 and z2 lie in the left half half plane, right? Z1 and Z2 lie in the left half plane. Why? Because if you see here, real parts are negative or 0. So real parts are negative or 0 is only possible when it lies on the left half of the plane, right? Then, then we can take a path, right? Also in the same half plane, okay? And for any z on this line, we have e power modulus z is always less than or equal to 1, right? Therefore, Therefore, integrating along this line, we get e power z1 minus e power z2 is less than or equal to integral z1 to z2 modulus e power z dz is less than or equal to z1 minus z2 modulus, right? So this is the proof. Okay. Now another problem. Let the points z1, z2, z3 lie on the unit circle of a complex plane and satisfying z1 plus z2 plus z3 equal to 0. Then prove that z1, z2, z3 forms the vertices of an equilateral triangle. So this is an exercise for you. Try to solve. Okay. So thank you very much. Thanks a lot.